Okay, I think we should start. Good evening, everyone. This week we are going to mostly talk about graph theory. I hope I'm audible. If not, you can put in chat. Okay, fine. So I hope you went through the lectures of this week. They were mostly related to graph theory, and we are going to look at a few questions from graph theory today. Uh, so it will be a good revision for you, and also if you didn't understand any concept related to graph theory, you can ask here. Okay, so like last time, we are going to start with a few problems. So look at this problem, which says that there is an undirected graph G on 30 vertices. So the root number of vertices are 30. In the undirected graph, there are 4 connected components. So the whole undirected graph G is not connected, but it has 4 separate connected components. And the question is, what is the minimum number of edges in G? And does it depend on sizes of the 4 connected component? So read the question carefully and try to answer which option can it be. Okay, so before answering this question, let me ask you one basic question. So if I've given you a list of 3 vertices, so the graph is made of 3 vertices, v1, v2 and v3, then what are the minimum number of edges that the graph can have? So if you have 3 vertices, v1, v2 and v3, and the graph G will have vertices and edges, so tell me what is the minimum number of edges that that graph can have? Think about it.
Do they all have to be connected?
And there are no other constraints on it, so it's just an undirected graph, and like it's not given that it should be connected or it should be any other way. What you are just given is the set V, which contains of v1, v2, v3. So you can see in the chat box, and I'm asking you what should be the minimum size of the set of edges that it can have. There is no constraint of it being connected or anything. Yeah. Okay. Yeah. So 0 is okay, and if you're not given any other constraints and you are given n number of vertices and you are asked what would be the minimum number of edges for a graph G with no constraint, then you do not actually have to have any edges. You can have just these three vertices on their own and none of them is connected to any other vertex. So in that case, your edge list would be a null list. It won't have any member, and the minimum number of edges would be 0 in that case. Alright. So here the diagram wouldn't be anything. Let me give you one. So here basically there will just be vertex v1, v2 and v3, and that is all. They won't be connected by any line, and they are just three disjoint vertices. They are not connected, so there are no edges basically. I hope that is clear. Apart from that, we are going to move to the next graph, which is called a minimal connected graph. So here you see a graph is shown, and this is a minimal connected graph. What is the definition of a minimal connected graph? A graph is said to be minimally connected if removal of any one edge from it disconnects the graph. So first think about this thing, that what would be a connected graph in this definition. So a connected graph would be one such that if you'll pick up any of the two vertices, so here we are given 6 vertices, and if you choose any of the two vertices like 6 and 2, let's say, then there is a path connecting these two vertices 6 and 2. So the path would be 2 to 4, 4 to 5, and then 5 to 6. Okay. So connected graph is a graph in which you, whenever you pick any of the two vertices, you are going to find a path that connects them. Okay. And a minimal connected graph is one in which if you are going to remove any of the edges, then the graph from connected it becomes disconnected. Now disconnected would just mean that there are pair of vertices which when you pick up you won't find any path between them. So for example, if in this graph we were to delete the edge 2 to 4, this one, the 2 to 4 edge, what happens is you won't have any path between 2 and any other chosen vertex. So if you choose 2 and 1, so there won't be any path, and 2 to 3, basically 2 with any other vertex, and there wouldn't be any path to it, and it becomes basically a disconnected graph. So this is a problem solving session only, Banwal, and we are basically discussing problems from the topics that were covered in the lecture. So if you'd go and watch the lectures that were there in the last week, so it was from graph theory, and these are the concepts that are already covered in the graph. So this is more like a revision for you, if you have seen the lectures, that is. Okay, so basically coming back to the question, now you know the definition of minimal connected graph. So now again look at the question here, and you are given an undirected graph G. You are given that there are 30 vertices and there are 4 connected components. In the 30 vertices, you'll see these 4 subsets such that these subsets are connected between them. Okay. And now you are asked what would be the minimum number of edge in the whole graph G. So think about it and answer. So now you know what is a minimal connected graph. If you'll go back here, you had 6 vertices here, and you count the number of edges 1, 2, 3, 4 and 5. Okay, so if you are given 6 vertices and you are said that the graph is connected, then the minimum number of edges it can have is n minus 1. You get it? So we have 6 vertices here, and to connect them, to make the graph connected, we need to basically have on a minimum 5 edges in the graph. Now you are given in the question, you are given the number of vertices are 30, So, okay, first answer me this. If you have 30 vertices and you want to connect the whole graph, so you do not have 4 connected components, instead you have the whole graph is connected, then what will be the answer? Yeah, vertex means nodes. Yeah. So if you were not given this part of the question, 4 connected components, and you are given that the whole graph is connected, then what would be the minimum number of edges to connect the whole graph? Okay, yeah, 29 is the correct answer. Now, if you think about this part, that now this graph is not completely connected, alright, but it has 4 connected components. Okay, now to get 4 connected components from these 29 edges, how many edges you can remove such that you will at least have 4 connected components still? So if you have 29 edges and you remove one edge, then what will happen? You will have 2 connected components. You remove one more edge from 28 to 27, you have 3 connected components. Okay, now from 27 to 26, you will basically get 4 connected components. You get it? So if you will look at the example graph that we have here, so for example we remove 2 to 4 here, the edge, then we have basically 2 connected component. One connected component is basically 1, 4, 6, 5 and 3, and another one is 2. You remove one more, let's say 3 to 4, you get 2 connected components. So now if you have 4 connected components, basically you have to remove 3 edges, and yeah, the answer will be 26. So look at this question again. If you did not understand any part of it, you can ask right away. Okay, I hope it is clear. It's a pretty straightforward question. Okay, then we'll move on. Okay, this is a pretty long question, but it isn't so difficult. Just read it carefully. We are given a graph G, and it is defined by its vertices and edges. So vertices would just be number. So these are nodes or vertices numbered from 1 to n, and E is basically an adjacency list. So it will just be basically list of vertices that are connected together. So let's say 1, 2, 2, 4 and 4, 8. So it will just say that 4 is connected to 8, or like 4 is connected to 8 in a directed fashion because it's a directed graph. Now you're given basically out U a list. So basically out U, U is a vertex here. So if you have out 2, let's say, then the vertex 2, whatever edges are going out from 2, like 2 to 3 or 2 to 4, let's say. So out 2 would be a list of those vertices. And from this list, now you are told to construct an NU list. NU would be like N2 would be all the edges that are coming into 2, like directed towards 2. So this would basically be a list of vertices such that these vertices have an edge connecting them to 2 in that fashion, directed fashion. So what you are asked is, if you are given this list out U, what would be the complexity of computing in U? Okay, read the question carefully, and I want you to attempt it first before I tell you the solution or methods to do it. The answer is in the terms of n and m. N is the total number of vertices you have in the graph, and m is the total number of edges. One good approach to do this question is to take a small graph, an exemplar graph, make it directed, put in some edges in it, and see what would the outlist look like. Okay, and from the outlist try to compute in list, and then you would get a feeling of what would be the complexity in terms of n and n. If you haven't understood the question to begin with, then you should ask either in the chat or just open your mic and ask your question. Like, it's important to understand the language of these questions also, because the language itself might look a little complicated, but if you're not used to these kind of language, then it's better to understand them right away, because these will be the same language used in quizzes and assignments and your exams. So it's better that you get a grasp on the language itself, like the notations, mathematical notations, or like the words like adjacency list and those kind of things. Yeah, out is also directed in the sense that out of a vertex is basically the edges which are directed outwards of u. So out of u would be all the edges that are going out of u to some other vertex, and it is basically a list of vertices. So let's say u is going out on u1, u2 and u3. So this u1, u2, u3 is out u, the list of vertices that have an edge with u, directed u to that vertex. Okay, so let's see the same question on a small exemplar graph. So let's say you have this graph given. It has 4 vertices and they are directed edges going out of each of these vertices. So the outlist here would be out 1. So if you see this vertex 1, so it has 2 edges going outwards towards 2 and 3. So out 1 basically would be just 2 and 3. Now if you look at out 2, so there are no edges that are going outward from 2. So there are two edges, but they are both coming inward. So basically out 2 will be a null list. There are no values in it. If you look at 3, then you have this outward edge and basically going from 3 to 2 and another outward edge from 3 to 4. So you have 2 and 4 in out 3, and similarly out 4 only has one outward edge going from 4 to 3, and you only have this one list. Now similarly, you are given this out list. What you have to think about is how are you going to construct the n list. So first think about what n list will be exactly. So in the chat, can you type what would n1 be here? What would be the exact n1, the list? Yeah, that is correct. It will be empty. What about n2? Yeah, it is 1 and 3. Okay, so you get the hang of it. Okay, now if you were to construct the same list using this out list, then what are you going to do? Like, just think about the algorithm in your head, like even how you would compute it yourself. So what you do is go on the first element, out 1. Okay, now out 1, you see that there is an entry 2. Okay, so what does this entry mean? That there is an edge from 1 going to 2. Okay, so now what are you going to fill? How are you going to use this entry to fill n? Basically, you know that there is an edge which starts from 1 and goes to 2. So you are going to come to n2 and put an entry 1 here. You get it? Because from the first list itself of out 1, you see that there is an edge from 1 to 2. So that means that 2 has an edge, inward edge coming from 1. So you are going to list basically 1 in this n2. Okay, and similarly you go on 3 and you see that there is an edge 1 to 3. So in n3 you put 1. Alright, so to fill this whole n list, you are going on each of this out 1, then you go on 2, and then you read 3. Then you go on out 2, there is nothing to read, you move on. You go on out 3, you read 2, 4, put them in the right place. Then finally go on out 4, read 3 and put it in the right place. Now you think about how many checks we have done in terms of the number of vertices, which are 4 here, and the number of edges, which are 5 here. So we go on the first vertex, then read the edges. We go on the second vertex, read the edges. We go on the third vertex, read the edges. We go on the fourth vertex and read the edge. Okay, so how many times you would be computing this? So we are going 4 number of times in each of these vertices. So that is 4, which is number v. Okay, and in the sense of the question, it is n. Okay, and on each of this we are going the number of edges that they are there. Okay, so if the total number of edges are 5, so here we have 2, 3, 2, 4 and 3. So these are like, if you look at the right side of out list, like the list, it has elements which are equal to total number of edges, which is m in our case according to the question. So from constructed this n list from the out list, you are basically going to each of the vertex and you're looking at all of the edges. Okay, so if you are to solve this question in an abstract fashion in terms of n and m, then basically you're going on each of these vertices and you're looking at all of the edges. So when the algorithm completes, you would have gone on all the n edges and all the n vertices and all the m edges. Okay, so to fill this complete n list from out list, you have to look at n vertices plus m edges. So the solution would be O n plus m. So just look at the solution and just think about how we did this on a sample graph here. and how does it translate to the abstract equation that we had before. Feel free to ask any step if it isn't clear. Okay. So in the example, basically we are given 4 edges and 4 vertices, and each of these vertices has some edges coming out or in. Okay, so we are given an out list which is basically out 1, and it is given the basically it's a list of vertices that has edges in the fashion 1 to 2 and 1 to 3. So basically out 1 will be the list of vertices such that 1 has outward edges to those vertices, okay, which is 2 and 3 here. Like if you'll see 2, it is basically a null list because you do not have any edges going outward of 2. Similarly 3 and 4. Now the question is, you have to construct like out 1, out 2, out 3, out 4, look at them and construct in 1, in 2, in 3 and in 4. And what would be the complexity of this thing? Now to construct this in list from out list, you have to look at each of these vertices, go over each of the edges that this vertex has, the outward edges, okay, and similarly you have to repeat it for multiple vertices, okay, and you have to go over each of the edges that they are constructing. Like if you'll see 3 has outward edges to 2 and 4, okay, so when you are constructed N2 would be basically edges that are coming inward, okay. So if you look at out 3, it will be basically outward edges from 3 to 2 here. So and this same edge will basically be in the list of N2, okay. So to construct N from out, you have to go on each of these vertices and read each of the edge values. So you would be reading the number of vertices, which is n, plus the number of edges, which is m times. So that brings O(n plus m). So Mihir, I hope your like question was clear. Like if you still have a doubt, like you can just switch on your mic and tell me what exact confusion you have. Ram is asking for each U and V, O, N, check edges, N. Yeah, basically that is the whole concept. Yeah, O(n plus m). Okay, fine. So still, if this thing is not clear, just give it another read and let me know if it is not clear. We can go over it once again. Okay. If it is clear, then we'll move to the next question. Just read this question. The question that is given here is a DFS tree. So DFS basically is your depth first search. So you look at a graph and you are visiting each of the node in the according order of their depth, okay. So that is basically depth first search, and in the order that you are visiting them, you can make a DFS tree. So basically in this question, D would have is visited first, and then you visit A, then basically B and E, then G, then F, C and H. So this is not the original graph, this is the DFS tree of the original graph. The original graph is GR. The number of vertices are same, but the number of edges can be different, okay. And looking at the DFS tree, what you have to figure out is which of these cannot be an edge in the original graph G. Okay, just read the question, try to think about it. Okay. Okay, let's look at what a DFS tree is first. So if you're given this graph G, okay, and we are doing a depth first search on it, okay, so we are starting at node A here, okay, and we are visiting, let's say, left nodes before the right nodes. So we are going to start with A, then we are going to do B, then D, and then F, okay. So tell me what would be, first tell me what is the order of visiting the nodes. So what you have to give me is an order of these vertices, and the order pertains to how we are going to visit them. So the nodes that we visit first is written first. And this is a depth first search, and we are visiting left nodes before right nodes. Okay. So I see most of you got it right, and there is one alternative answer that is floating around, and I'll just explain you why that is not true. So the correct order is this: A, B, D, F, E, C, G. Another possibility I see floating around was F. So you are visiting basically A first, then it is depth first search. So you go to B, and then you go to D. You're going as deep as you can before increasing in your breadth. So once D is reached, you go back to B, then you go to F, and then you go to C or E. So some of you has written C, but you would actually go basically as many layers as you can go down below. So even though in representation you see that E is coming above it, but if this is only a visual representation, in the graph theory, in those notations of graph theory, you basically visit all the nodes that are connected to the previous node. So if you are at F, then before traversing back to A and then to C, you are going to visit all the nodes that are connected to F. So once you have visited B, you go D, then you go F, and then you go E, and then you go back to A and then to C and G. Okay, if this part is not clear, you can ask me right now.
So I had a doubt. I don't
Yeah.
understand why we visit E after F. Shouldn't E be, isn't E at a higher level than F?
Okay.
E there? Yeah,
Okay. So I told you two things for this question. This is a depth first search, and we are visiting left nodes before right nodes.
right.
So this is a depth first search, and we are going to visit B from A, then we are going to visit D, and then we are going to visit F. We are not going to visit C because F is at a lower depth. Then,
Right.
yeah.
No,
So,
so my question is like, okay, A, B, D, and
mhm,
then F, right?
yeah,
And then should it be C and G? Like, why is it A, B, D, F, and then E? Like, that's what I want to understand.
because you are prioritizing depth before left or right. So once you are going to cover depth for every node. So if you had
Mhm.
A, then you are going to B. Okay. Now at this point you are going to D, right? You are not going to C. Okay.
Yes.
Or even when you are at D, you're going to F. You're not going to C from here because you are covering as much depth as you can. So you are going to visit all the nodes that are connected to the node that you're visiting first before moving up, basically in hierarchy.
Correct, correct. No, so my doubt is, so I understood up to F, like first four letters are fine, A, B, D, F is fine.
Yeah.
So like after this, why does E come first? Shouldn't it be C and G? That's depth, that's left to right depth first, right?
Okay, so I think what you are thinking is that the depth of E is higher than F.
It's yes, that's right, correct.
Yeah, but that is not the question. So that is not uh, how you actually compute depth. So the depth is marked with A. So you start with, let's say, 0. All right. Then you
Mm.
move to B and you mark it 1. Okay. You
Mm.
move to D. Then you mark it 2. Then you come back to B. Then you again go to F. So F will be given a depth of 2 because B has a depth of 1. Okay. Then from
Correct.
F to E, you're going to mark it 3 because F has a depth of 2. So the
Oh,
depth
okay.
isn't how it's visually represented to you. It's not how you look at it. It's basically, depth is basically what would be the order of reaching these nodes if you're just moving edges to edges, like if you're just looking at connection. So F here was already marked 2, and from F you can move to E because you have to basically traverse this edge. And because you traverse this edge and you're coming from 2, then you're going to mark E at a depth of 3.
That makes sense. Got it.
Okay. uh, Before we move on, this was a graph G and this is the order of the traversal. So what I want you to do is make a DFS tree of this graph. What would be the DFS tree look like? Okay, so I hope you got a chance to attempt it. You don't need to type in the answers, you can just make it on like a piece of paper or something, and I'm just going to show you the answer, you can just verify with it. Okay, so it will look something like this. So if you look here, basically we have A, the node that we reach first, then we have B, then we go to D, and then we have F, alright, and then we move to E. Now E you can place right or left, it doesn't really matter here. Then we move back to A, then we visit C, and then we visit G. Then we move back to A, and because we have already visited E, we do not visit it anymore, and that is the end of our algorithm. So this would be the DFS tree of this graph G. Okay. Just look at it carefully, see if it makes sense. If it doesn't, ask me right away. Okay, so given this information, attempt the question again and tell me which of these edges cannot be there in the original graph G given the DFS tree looks like this. Okay, so many of you did answer it correctly, AC. Why the answer is AC? If you'll think about it, so you are given this DFS graph, and in the original graph, if A and C were to be connected, then basically after you have reached A, then B, then E and G, then you come back to B, then A, then you would have gone to C. You wouldn't have gone to D, then F. Okay, so basically you can only have a descendant connected to its own ancestor for a DFS tree. If you want to put it into a comprehensive statement, that would be it. So A and C here are on two different right and left side of D. So it cannot happen that you are going to move to D and then to C. Basically, if A and C are connected, you are going to visit it first. As we saw that we visited E in the previous question. So it is basically just this question. So if this F and E were not connected here, then of course E would have come as a descendant of A, but because F and E were connected here, then E just comes after F. Okay, it cannot happen that now E is going to come on the right side of A, basically. So if the answer, the solution or anything is not clear, just ask right now before we move on to the next question. I see only a few people attempted this question. I got a lot of answers before. I hope it's clear, like don't get confused about it. Okay. So the whole question is that you are given a DFS tree, and what you have to do is basically look at the list of edges that are given and see what can be possible edges and what cannot be possible edges for the original graph G. Okay. So if you look at D and E, okay, let's say, so basically your D and E can have an edge, okay, like you can just connect it here, like in this graph itself, D to E, and with that connection you can still have the same given DFS tree, like you can move to D, then A, then B, and then to E, okay, because E is connected to B also, okay. So D and E can be a possibility. Similarly, D and H, with the same logic, if D and H you connect it here, then it can happen that basically you are going to reach H with F first before D. So if you just connect D to H here, you'll still reach H after reaching F. So you reach F, then C, then H. And then you do not connect this D to H, but D to H can be an edge. Similarly, A and G can also be an answer, but if you look at A and C, so if you connect, let's say, A and C in this graph itself, then what happens is you start with D, then A, then complete this whole lower tree B, E, G, and then you move to C. So basically C comes as a descendant of A. You do not go back to D without finishing up all the descendants of A. Okay, Surya, I hope that was clear. Like if you still have a doubt. Okay, fine. Okay, let's move on to the next question. There are a lot of time also. Okay, this is a little, yeah, this is an interesting question, and it's actually fun to solve. So what you are given is a directed acyclic graph, okay, and you have to do a topological ordering of this graph. So I hope you know what directed acyclic graph is and what its topological ordering is. Okay, it's basically setting all of these nodes 1 to 10 in a line. We'll just put them in a line, and then in the line all the edges would go forward, in the sense that the nodes that come before in the line are going to be connected to the nodes that come after them. Okay, and what the question is, how many such orderings can be there? Okay, and you are given these two constraints. So essentially you need to just figure out what are all the possible topological orderings you can have here, and from that total number you have to subtract the orderings which do not satisfy the constraints that you are given. Okay, so forget about the constraints first. Like first just think about what can be the total number of topological orderings that this graph can have. Okay, and before I tell you any more information, just attempt it. If you guys already know what a DAG and topological ordering is, and if you can indeed solve this question, then forget about the particular question. first I want total number of orderings that it can have, so you can just put that in the checkbox, like if you have figured it out. Let's look at the total number of possible orderings before, and then we'll talk about the constraints here. I'll give you guys another minute, just think about it. I want you to think about this first, like solutions you can get online also, but it's important to basically figure things out for yourself. That's how you understand it really. Let me give you some information about what this DAG and its topological ordering means exactly. Okay, so this is the graph that we are given. It's called a directed acyclic graph because if you take any pair of vertices, you're just going to get at most one path from that. So if you take, let's say, 1 to 8, alright, so you basically have paths going forward 1, 2, 3, 6 and 8, 1, 4, 6 and 8, but you do not have any path that comes back from 8 to 1. So there are no cycles in the graph. So there are only paths that are going forward and they are not going backward. Now because of this property, what you can do is write these nodes in a line like I said before. So here you have basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you call these permutations of the nodes as orderings. Okay, and it will become a topological ordering if you have edges that go only in the forward direction. So if you will look at this current ordering, which is just 1 2 3 4 5 6 7 8 9 10 written in order, then you see if you now fix any edge to it, then you will have edges 1 to 2, then 2 to 3, okay, 1 to 4, then 4 to 5, okay, and 3 to 6. So you see any of the edges from the above graph are only going to come from backward to forward, okay. So you have nodes which are backward relative to any of the node which are forward, and you'll have an edge between them. Any edge is going to connect backward node directed towards forward node, so that will be a valid topological ordering. So first what I want you to do is just tell me if the current order that is written, is it a valid topological order or not. Okay. uh, okay, I'm getting answers here. People who are writing it's not valid, you have to write the edge that is going to break the ordering. So if you think that the ordering is not valid, also accompany it with the corresponding edge which is actually going from forward to backward rather than backward to forward. So the no edge has to go from backward to forward. So Ram, you are saying 1 2 and 1 4, and 1 2 will go from backward to forward, and 1 and 4 is also going backward to forward. So these two edges at least seem to be working. Same is the case for 2 3. There is no edge 4 and 2, so Vaishnavi, you only have to name valid edges in this graph G. Yeah, so 2 to 3 is a valid edge, but again it is going from backward to forward, so it isn't really breaking the order. Yeah, we are not talking about the constraints right now, Ram. So what we are discussing is just if the given topological order is valid or not. If all the edges from the graph above are actually in the order from backward to forward. We're going to look at the constraints also. We're going to talk about it, how it changes the question. Now this is only one such valid topological order. It is indeed valid. If people have a doubt about it, you should really ask right now. This is a valid topological order, but this is not the only one. So what Ram, you are asking 4 before 3. So in this one, if 4 actually comes before 3, then you'll see all the edges are again going from backward to forward. So it is indeed a valid topological order. So the topological order is not a unique permutation. There can be various permutations that satisfy the topological order. So here, as Ram pointed out, if you were to exchange 4 and 3, you will still get a valid topological order. What are the only constraints then we have right now? Okay, so we have to have 1 placed at the very beginning. If we place 1 anywhere else, then it will break the topological order. And how do you quantify this thing? Is basically you calculate this n degrees and out degrees. Okay, so if n degree means edges coming inside the node, so the n degree of 1 here is 0 because there are no edges coming inside. Okay, so if you have any node with n degree 0, there are no edges that come in, so that node you have to you have to surely place it in the beginning of your order. Similarly, out degree is defined as number of edges that are going out of your node. So if you look at 10 here, okay, so 10 basically has an out degree of 0. There are no edges that are coming out of 10. Okay, so basically 10 has to be written in the end. If you put 10 anywhere before that, then let's say we exchange 9 and 10 here. 10 is written second last and 9 is written last. Then you have this edge 9 to 10, and 9 to 10 is actually going backwards, and we do not want that in the topological ordering. So we have the constraint that 1 has to come at the beginning, 10 has to come at the end. Okay, for any valid topological ordering. Okay, now what about 6? Can you move 6 from this position really? Now 6 basically has two edges coming in from 3 and 5, okay, and two edges coming out to 7 and 8. Okay, so if you will try to put 6 in any other place, if you replace any other place, then you're going to find that you're going to break the topological order, because let's say we exchange 5 and 6 here. Okay, then the edge 5 to 6 will actually start coming backward. Okay, similarly if we let's say switch 6 and 7 here, then the edge coming from 6 to 7 is now, it is actually in forward direction. Now if we switch them, it's going to be in backward direction. Okay, so for a valid topological order for this given graph without any constraints, we have this as possibility. So 1 necessarily has to come in the beginning, 6 has to come in the end, in between at this position, and 10 has to come at the end. Okay, now you have 4 position here, 2, 3, 4, 5, and you can change these position, and 7, 8, 9 you can change these positions. So first what I want you to do is tell me how many possibilities can you permute these 2, 3, 4, 5 with. How many possible permutations will be there such that the topological order will be valid. So how many possibilities just for this thing, 2, 3, 4, 5, forget anything else, just this 2, 3, 4 and 5. How many possible, and how do you exactly compute it? Like if you have like some formula for it or anything, you can just count them also. Okay. Do you guys need another minute to try it, or just think about how many possible permutations you can make with these 4 digits? Okay, so given the 4 digits, if you will forget about everything and you just think about total number of permutation that 4 digits can take, then that number is 4 factorial. Alright, comes out to be 24. But if you will look at all those 24 permutations, then you will find that many of them do not satisfy a topological order. Why? Because you have a constraint here that 2 should always come before 3 in this ordering. So let's look at the first order that we had here. Like we have 1, 2, 3, 4. So 2 is coming before 3, so the edge goes from 2 to 3. If we switch this 3 to 2, then you are going to be in trouble because you'll have 2 to 3 coming backwards. Okay, and you have another constraint 4 to 5, so 4 should always come before 5. So a good way to count this is without actually enumerating it. So you are given 4 boxes here. Okay, now for 2 3, let's say that you want to place 2 3 in these 4 boxes. Okay, how can you place 2 and 3? You choose 2 boxes out of these 4. So let's say out of these 4 boxes I chose the first and the third box. Okay, for 2 and 3. Now 2 and 3 are going to come in first and the third box only, and because their order is already fixed, 2 is come before 3, so you'll have 2 in the first box and 3 in the third box here. Okay, and then 4 and 5 can only be in this one and this one box because 4 has to come before 5. So essentially what you're counting is number of ways to pick 2 boxes out of 4 boxes. So your answer is 4C2 here. Okay, and these are your possible permutations: 2 3 4 5, 2 4 3 5, 4 5 3. In each of these permutations you'll notice that 2 comes before 3 and 4 comes before 5. That is the only constraint, and there are 6 ways to do it. Now similarly, give me the correct number for your second set, 7 8 and 9, and I want a number in terms of the combinatorial notation, the C notation. Give me an NCM notation. Okay, so your total number of boxes are 3 here. You can either choose 2 boxes for 8 and 9, or you can choose 1 box for 7. So answer will be 3C2 or 3C1. This is correct, people who attempted it. So you have these 3 possible permutations for 7 8 9. Okay, notice 8 always comes before 9, otherwise your topological ordering breaks. So the possible number of topological orderings then would be 4C2 into 3C2, which is 6 into 3, 18. Okay, now what I want you to do is read the question carefully once more and apply the 2 constraints that are given here. Okay, and the question is, it should satisfy one or both of the following constraints. So even if a topological ordering satisfies one constraint but doesn't satisfy the other, it's okay, as long as it satisfies at least one. And now tell me what would be the final answer of this question. Total number of orderings are 18. You have to remove topological orderings which do not satisfy the constraints, and you have to basically remove the topological ordering in which both of the constraints fail. If anyone satisfies, it's okay. You have to remove the orderings in which both of them are breaking. Okay, I only got one answer, and let's look at it. So you had these possible orderings here, and your constraint is that 4 appears before 3. Okay, so the constraint will break if 3 appears before 4. And let's count how many orderings have 3 before 4. So you have only one ordering here, 2, 3, 4, 5, which has 3 before 4. So only one ordering that breaks this constraint. Then you have 8 appear after 7. So 8 appears after 7. So 879 and 897, these two orderings break the constraint, because here 8 actually comes before 7 and we want 8 to appear after 7. So in total, 1 into these two possibilities, you will have 2 possibilities out of the 18 possibilities which will not satisfy your constraint. So your final answer would be 16. If you didn't understand this question or the solution, just ask right now. Okay, in case there are no questions about it, if there are, you should really ask. But if there are no questions, there is one more problem on the slide, this one. I want you to attempt it. There will be a solution of this problem also in the slides itself. And just attempt it, it's a fun problem, quite easy. And in case you didn't understand it, you can ask on the WhatsApp group or on discussion forum or when we meet next time. If you have any other questions regarding graph theory, you can post it on WhatsApp and I'll have a look there. Okay. We have run out of time, so we are going to end the session right now. In case you have any questions, you can ask.